Okay, so good morning everyone. So in the last class we have discussed about the Biot-Savart's law. Okay, so the introduction of the magnetic field, then we have discussed the Biot-Savart's law. Okay, then we have come to this particular equation, okay, of Biot-Savart's law, and the consideration that if the current carrying conductor, because in magnetic field we don't use any pole, because in electric field, when we discuss or any when we come across any particular you can say law of electric field intensity or a Gauss law, Coulomb's law, so we generally consider a point charge. Okay, in magnetic field similarly there are also magnetic field intensity, okay, magnetic flux density, then we have the magnetic force also. Okay, so we have the magnetic force also. Then all these things we consider or we derive or come across by not using any magnetic pole. Okay, because we know that in magnetism unipole does not exist, because you cannot take a single north pole or a single south pole. You have to take a pair of poles. Okay, so the same expression can be or same you can say the laws can be derived using magnetic poles also, but since we are dealing with electromagnetism, so we consider a current carrying conductor. Okay, we call it a magnetic element. Okay, that is, we consider a conductor like this, which is carrying current I, okay, of say infinite length or any length, capital L. We take a small portion of the capital L, okay, and the length is dl, suppose. Now current, if it is I flowing through the conductor, so across that small part dl also I will flow. Now this is actually the magnetic material. Okay, this IDL will be considered as a magnetic material, this one, or you can say the current material or current element, differential current element, which will be considered as a magnetic source, because we know that a current carrying conductor, okay, has some magnetic field lines like this, okay, which is circling as if you are pointing the thumbs towards the direction of the current, and the fingers, the direction in which the fingers will be curling is the direction in which the magnetic field lines will be created, and H is the magnetic field intensity. So we know that similar to electric field intensity, when we have an electric field, and in that electric field we will have electric field intensity at every point. Here also the magnetic field will be created by the current carrying conductor, and some electric field intensity, magnetic field intensity is been pointed out over here, okay, which is dH. Okay, so we have this equation we have already derived in the last class. Okay, and considering some current carrying element, okay, differential current element, we have also considered a two-dimensional surface also, because a single conductor, if you take current I is flowing through a distance dl, if you take a two-dimensional sheet of conductor, okay, surface, okay, so this is called the surface element. So it won't be called line current, okay, it will be called surface current. So in that case the current will be I, but since it is multiplied with the surface, because you have to take or consider this in this way, that IDL, if you see this equation, IDL should be almost equals to KDS, almost equals to JDV. That means you will replace IDL with KDS. Now if you replace IDL with KDS, then what is K actually? IDL is equals to KDS, suppose, because you are replacing the same thing. So we know S is meter square and DL is in meter. This is in meter and this is in meter square, so they cannot be equal. So if this is ampere meter, so this unit also has to be ampere meter. But actually what we are getting this to be, this is meter square, isn't it? This portion is meter square, so K should be ampere per meter. So the value or unit of K should be ampere per meter, so that once they get multiplied, it becomes ampere meter, because it has to be equal. Okay, so that means I, or you can say K, okay, K is equals to I by dl. I by dl. K is equals to I by dl, or I by some length, because IDL is equals to I dl by dl, so it will be dl square, dl into dl. Okay, I can write this. I can write IDL equals to I dl, or if I write in this way, It will be easier for you to understand. Okay, I continue this in the different app. Okay, so that is easier to erase. Okay, so ideal, I can write ideal like this. Ideal, dl by dl, I can write like this, or I by dl into dl. Okay, I can write this. Now this I by dl into dl becomes dl square. So I call it ds, because dl square means meter square, so meter square means area. Now I by dl is equals to k, which is the current density. So that means this is the current density. K is the current density. So it is ampere by current. Ampere by length. Okay. Same thing for J also. Okay. If I do the same thing, if I take in this way, dl square like this. So it is dl square. Okay. This is dl cube. This becomes dv. Okay, this becomes dv. So this thing becomes dl square. So it is J, that is ampere per meter square. So J's unit is ampere per meter square. Okay, so it is current density, surface current density, J. That is why we can replace like this. Ideal we can replace with kds or J dv. That means a current which is passing through a conductor length dl, which is similar to a sheet, okay, two-dimensional, where the area is ds, total area is s, and this portion is ds. Okay, this portion is ds. So the current is I, but we are multiplying with respect to k, that is current per unit length. Okay, per unit length, because this is one length, this is one length. Okay, in area, this is the small area dv, because the entire area is v and the small area is dv. So the current will be I. So we will take J, that is current per meter square. Okay, current per meter square. So it is actually current per area into volume. Will give you the same ideas. Okay, so as an example, let us apply equation number 6, okay, that we have achieved, that is this one, with the Biot-Savart law with respect to current element, you can say line current. So as an example, we determine due to the straight current carrying filamentary conductor of finite length AB. Suppose there is a conductor which is along the z-axis, okay, z-axis. So now the conductor is not starting from the origin. Suppose the conductor is starting from A to B. Okay, the conductor is starting from A. That means the length of the conductor is over here. If I highlight with some other color, this is the conductor. Okay, this one. This is the conductor. Okay. We assume that the conductor is along z-axis with its upper and lower end respectively, subtending an angle alpha 1 and alpha 2 at P, the point at which H will be determined. So suppose H is at a point somewhere over here, H, okay. So we know that it is having a magnetic field like this, it is circling like this, magnetic field is created. So somewhere over here also it is created. So it is entering, so it is cross. Since it is entering, it is cross. Okay, it is like this. And somewhere over here there will be a dot which is coming out. Okay, this is the convention. Now this point is over here, so that is why we will draw, extend this at this point. We will see that this is not in line with this A. There is some angle. So if we extend this, we can say that alpha, this angle is alpha 1 and this middle one is alpha 2. Okay. Upper end and lower end, sorry, this is alpha 2, this is alpha 2. Upper end is alpha 2, lower end is alpha 1. This one is alpha 2, this is alpha 1. Okay. So if I clear this part, since you have understood. Okay, these are two angles. Now the thing is that particularly we note should be taken of this assumption as the formula to be derived will be applied accordingly. If we consider the contribution of H or dH at P due to the current carrying element L, so we know this equation, current carrying element L. Now it is actually in the z-axis because we know dl. Okay, current element dl, actually dl, the length is a vector. So if it is a vector, it will be represented in vector form, obviously vector form. So r will be also the distance from midpoint, because r is the distance from the midpoint of the current carrying element to the point P. Okay, now this has to be represented in the z-axis. So length is z. That means the point A, or because the midpoint is z. That means starting from origin to midpoint, it is z. Why we will consider the midpoint? Because we always consider the midpoint in case of any, you can say, relationship between two different bodies or two different points. Because point is a single point, but whenever we take a surface or a volume, and there are two volumes, okay, or two surfaces or two lines separated, two different entities, so we connect the midpoint to midpoint, okay, of the corresponding entity, or you can say element. So the midpoint of this particular length is over here, and the distance from the midpoint to the point P is r, and the distance from the origin of the Cartesian coordinate system to the midpoint is z, suppose. Okay. Now we consider that dl is equals to dz. Why dz? Because it is actually in the z-axis. So we represent dl in terms of vector. Since it is in the z-axis, so it will not have any x coordinate or y coordinate. That means it will not have any x unit vector in the x-axis, nor a unit vector in the y-axis. So it will have a unit vector in the z-axis. So this is the z-axis unit vector. Okay. So now r, the length r, okay, r is represented as rho unit vector rho minus z unit vector z. Why? Because it is assumed that this particular surface, okay, this is, since it is, you can see this is in a cylindrical shape. This is in a cylindrical shape. This is in a cylindrical shape. Okay. So if it is in a cylindrical shape, so we will consider that it is creating a cylinder like this. Okay. So we will consider a cylindrical coordinate system. Now we know the cylindrical coordinate systems have rho, phi and z, three coordinates. This is known to us. Okay. So this is actually rho, this is phi, this is z. So now the distance between midpoint to this particular point P, okay, is r. Length is r. So we will take the length in the Cartesian, not in the Cartesian, in the cylindrical coordinate system to be rho unit vector rho minus z unit vector z, because r is the length and it is a vector. So dl cross product with r gives you rho dz unit vector rho, unit vector phi, cross product. Why it is like this? Because cross product, we know that whenever we take a cross product between two vectors a and b, okay, suppose this one, so the resultant will be a cross b, vector will be mod of a into mod of b multiplied by sine theta, that we know. But one thing also to be noted, that there is a unit vector also. unit vector. Which is a unit vector? Because the resultant is a vector, so it will have a unit vector, and the vector is perpendicular to both the axes. So we know that if the unit vector, if you are multiplying or finding the cross product between two vectors, and the cross product, after the cross product, okay, the solution comes such a way that these two parameters, z axis and z axis, is common, but with respect to z axis and rho axis, okay, because z cross unit vector rho cross unit vector z gives you unit vector phi, the third axis, okay, it gives you the third axis, okay, it gives you the third axis. So hence this is represented as rho dz, because rho is the magnitude, dz is the magnitude, and unit vector phi is given, okay, the resultant, you can say the normal, okay, the resultant vector. Hence our equation, which was previously this one, equation number 9, we will replace the dl cross r with this solution, okay, dl cross r. Now we know that if this is dl cross r, then r cube will also be replaced, r cube. Now if you remember this particular equation, this here you can see there is no unit vector. In this equation there is no unit vector. So how can we replace unit vector? If you can remember, you can replace the unit vector like this, okay, unit vector like this, but generally unit vector, if you represent in terms of vector, it becomes cube. So here what we will do, we are representing in terms of cube. So the denominator, this part, I am once again going over here, this part, this r cube is not the vector, this is the magnitude of r, because r is the vector, r is actually the vector, it is the vector, okay, and r which is written is italics, it is actually the mod of r, okay. So this one is the mod value, okay, mod value. So mod value means, what will be the mod value of this? It will be this one, rho square root over of rho square plus z square. That is why it is written as 3 by 2, because it is root over, actually it is root over square root, so it is 3 by 2. Now if you want to calculate the value of h, okay, because it is the integration is there as per the equation, because we are representing for the entire length of the line, because what we have done, we have taken a small length, this one. If you can, if I remove this or erase these lines, wait, okay, okay, so if I remove these lines, so you can see this is dl over here, dl is there. That means we have taken for a small portion. Now to find the total h, because dh is for dl. Now total h, okay, will be equals due to the total line length l, okay. So it is integration will be there. For h, it will be integration to the small part, because this is dh, and integration to dh will give you h. The integration will be from, see, this is the unit vector which is there, unit vector is with respect to phi, okay, phi axis. So we will take the integration in the phi plane, that is from alpha 1 to alpha 2, okay, from alpha 1 to alpha 2. We will take this unit vector, we will take this integration. So once we put the values of alpha 1 to alpha 2, we will, because we will integrate, we will integrate with respect to the this one, dz is there, okay, with respect to dz, and we will put the values. So once we put the values, we get rho square cosec square alpha d alpha, okay, because we are representing with alpha over here, okay. How? Because see, let z is equals to p cot alpha, a rho cot alpha. See, let me explain. See, this is quite in with respect to trigonometry. See, this is the right angle triangle, okay, this is the right angle triangle. Now this length is z. Why z? Because we have considered z over here, because from the origin, this one, from the origin to the midpoint, the length is z. Okay, this length is rho. Why? Because we know in a cylindrical coordinate system, when we consider cylindrical coordinate system, okay, when we represent with respect to a Cartesian coordinate system, so this particular radius is the rho. Okay, so this is the rho, this one if you plot over here, this plane is the phi angle and this height is z. This is known to us. Similarly, if you consider a cylinder over here, if you consider a cylinder like this, same thing. So this is the radius rho, okay, and over here also this is the angle phi, okay, and length is, height is z. Suppose this is the cylinder over here up to here, cylinder. This is the length of the cylinder. So the angle will this length will be rho, and this is z, and this is r. Okay. So what is the relationship between z and rho? If this is alpha, because this will be base. Let me represent over here. This is base, this is perpendicular, this is hypotenuse. Okay. Now we know that tan alpha is equals to perpendicular by base. That means rho by z. Okay. So z is equals to rho into tan alpha. Oh, sorry, 1 by tan alpha. So 1 by tan alpha means cot alpha. So it is cot alpha. That is, it is written as rho z is equals to rho cot alpha. Okay. And dz is because the z, okay, the z parameter. What is z? Base. Okay. In this case it is base. Now if we take with respect to cosec square, that is the sine square. Okay, so they've taken the relationship between sine. Okay, so rho and z. Okay, rho and z. Once again, rho and z. Okay, yes. Now if you differentiate this equation, dz, if you differentiate with respect to alpha, okay, that means the derivative of cot alpha, that is minus cosec square alpha. So that is why if you find the derivative, then you will get this solution. Dz equals to this one, minus rho cosec square alpha d alpha. Okay, because we have to replace them, isn't it? We have to replace dz. So because in our equation we have dz with us, so we are replacing dz with this equation. That is why we are getting a minus sign, and 1 by 4 pi is taken outside. Okay, then we integrate and we get the solution. This is the value of h. Okay, so this is the value of h. So this expression is generally applicable for any straight filamentary conductor of finite length. Note from equation 12 that h is always along the unit vector alpha, phi. Okay, along the concentric circular path. That means it is along the concentric circular path of a cylinder, because alpha is the angle, okay, of the plane, angular plane. Okay, so now yes, so it is along the circular plane. So as a special case, when the conductor is semi-infinite, so that point A is now at the origin while point B is infinity. That means suppose point A is at the origin, semi-infinite. Semi-infinite means it is represented in such a way that this point A is over here and it is infinitely long upwards. B is somewhere at infinity. B at infinity. So it is infinitely long. Okay. So in that case, this total equation of H depends on alpha, so alpha 1 and alpha 2. So alpha 1 will be, in this case, alpha 1 will be 0 and alpha 2 will be 90 degree, because it is infinite, so it will be 90 degree. So if this point B is increasing, so the angle, okay, sorry, alpha 1 will be 0. Yes, alpha 1 will be 0. Oh, sorry, alpha 1 will be 90 degree actually. Alpha 1 is 90 degree. Yes, this is 90 degree. Alpha 1 is 90 degree and alpha 2 will be 0, because the more is the line length, the less is the angle. So if it is infinite, so it will be like this, almost 0. Alpha 2 is almost 0, like that. Okay. So the equation will be replaced. So if you put 90 degree 0 over here, 90 degree over here, you will get this equation. And if it is totally infinite, that means here also it is infinite. This is also infinite. So both the angles will be 0. If both the angles are 0, so this is also 0, this is also 0, so it will be, actually it will be, minus infinity. This is minus infinity. This is minus infinity actually. So minus infinity means it will be, you can say, the angle will be written as alpha 1 is 180 degree. So it is 180 degree. It is 0, so it will be 180 degree. Because you cannot represent both as zeros, because if the line is infinite and we have a point over here very close, so if this is almost equals to 0 degree, this will be almost equals to 180 degree. Okay, this angle is 180 degree, this angle is 0. Okay, of the two directions. So that will result in this solution, that this value will be 1, and this will be minus of minus 1. So the result will be 2. Okay, so this 2 will be cancelled. So this 2, if it is cancelled, then you will get this equation. Okay, so this is the case for a infinitely long conductor. Okay, this one. To find unit vector in equations, that is 12 and 14, okay, in these two equations, in these two cases, is not always easy, because a similar approach where the 5 unit vector will be equals to unit vector L and unit vector rho, where unit vector L is unit vector along the line current and rho is unit vector along the perpendicular line. Okay, that means this perpendicular line, this is the perpendicular line and this is the length. So same thing, because phi, we know phi is represented as rho cross z. So since this is in direction of, this is the length, so we will represent that unit vector L. Same thing you can represent, okay, that, but you can represent with respect to z also. Okay, so this is not important. So important part is that if you have a current conductor, okay, and if you know the equation of dl, so if you want to find out the actual value of L, then how to integrate using the vector analysis, that is shown over here. Because in this case we have to always consider the cylindrical coordinate system, because this is in the shape of a cylinder. Why? Because the magnetic field is circling in this direction, so it will always be in the shape of a cylinder. So every point wherever you will find an value of H, okay, it will be within the cylinder. That is why you have to take the cylindrical coordinate system. Now this is the application. Now you can say why we are studying cylindrical coordinate system, because the application of cylindrical coordinate system is in the Biot-Savart's law. Okay, because in the Biot-Savart's law, the magnetic field intensity, okay, it will always circle. So in its own reality, it is only existing within a cylinder. Okay, so in its world it is just a cylinder. So that is why the Cartesian coordinate and the spherical coordinate system, that analysis won't be considered. Okay, so there is a numerical simple one. Let me explain this. So the conducting a triangle loop. Suppose we have a triangle loop like this. Okay, triangular loop. That means this is a conductor, a current. Sorry, certain circuit. Okay, circuit like this, which is shaped in a triangle. 3 wires are there. 1, 2, 3. 3 are connected in a triangle. This is placed in the x-axis. Okay. Now this length. Okay, length is 2. Okay, and they are actually the shape of a equilateral triangle, I think. Okay, so it carries a current 10 ampere. Okay, so find H at point 005 due to the side 1 of the loop. That means we have to find H at 005. So 005 means in the z axis. Actually it is z axis. This is represented wrong over here. This should be z axis. Okay, so 005 means this is 1, so 2, 3, 4, 5. At this point you have to find out the value of H, which is just represented over here also. Okay, so you have to find that particular value of H at that particular point due to the side 1. That means not due to all the current conductors. No, only side 1, because these are imaginary now, because they don't exist. Suppose this is there, but the impact of H at this particular point we have to find out for 1 only. That means side 1 only. That means obviously if you have a conductor of a triangular shape, okay, then whatever magnetic field it will create due to the whole conductor, but we will consider the magnetic field due to this particular conductor only at this point, because actually at this point the magnetic field, total magnetic field will be due to the contribution of all the 3, but we have to only isolate that portion of magnetic field intensity which is due to this current carrying element of side 1. सिर्फ उसका जो कंट्रीब्यूशन है वो निकालना है, बाकी का नहीं निकालना है. उसको बाकी को सेपरेट करके इसको अलग से निकालना है. Now you can see, since the current is flowing in this direction, so if you put your thumb in the direction of the current, so the magnetic field lines will be circling like this, isn't it? So the direction will be, now tell me, in this point, okay, suppose this is point P, whether you will have a dot sign or a cross sign. Which one? Dot or cross? कौन सा देंगे यहाँ पर? ये जो है इसको डॉट लिखेंगे या क्रॉस लिखेंगे? वो डिपेंड कर रहा है. डॉट. क्यों?
क्योंकि सर हाथ को घुमाने पे आउटसाइड आ रहा है.
हाँ, outside. So it is outside the page, because if you point your thumb, okay, in this direction, so the fingers will be curling like this. So it will be like this. So यहाँ से डॉट होगा, क्योंकि ऐसा है कि यहाँ से ऊपर निकल के फिर यहाँ पर आ रहा है ये, तो ये कहीं पे क्रॉस होगा, ऐसा है. ठीक है, ये इक्वल लेंथ नहीं है फिर भी. ठीक है, गुड. सो that will be dot conformation, cross conformation. So you have to find the value of H at this point. Okay, now we will proceed in this way, because here also we will consider the cylindrical coordinate system. Okay, now cylindrical coordinate system, अगर पहला वाला न्यूमेरिकल देख लो, ये वाला, यहाँ पर क्या था? यहाँ पर सर्कल और सिलेंडर था इस डायरेक्शन में, है ना? तो सिलेंडर ऐसा था. सो ये रो था, रेडियस. ठीक है, ओके. सो यहाँ पर कैसा हो रहा है? यहाँ पर जो है सिलेंडर ऐसा बन रहा है. ठीक है, सो सिलेंडर जो होगा, इसको मैं रिमूव कर रहा हूं, इसको रिमूव कर देता हूं. तो सिलेंडर जो है, स्ट्रक्चर जो है, वो ऐसा सर्कल करके बनेगा ना, ऐसा सर्कल करके बनेगा, ऐसा. तो मतलब इस पॉइंट पे, तो इस पॉइंट पे अगर हो रहा है तो ऐसा सिलेंडर होगा, यहां से यहां तक सिलेंडर होगा, है ना। तो डिस्टेंस जो है यहाँ से, मान लो कि यहाँ से ओरिजिन में है, अगर या तो पेज खत्म हो गया इसलिए मैं दिखा रहा था, तो रेडियस जो है वो इस डायरेक्शन में है, रेडियस, इसलिए इसको रो दिखा गया है, रो। So this is the radius. That is why we will take this z axis to be the rho axis. Okay. That is why it will be the rho axis. So obviously it won't be z axis. Okay. So कार्टिशियन कोऑर्डिनेट, क्योंकि हाँ अलग से हो जाएगा कि एक्चुअली मान लो कि तुमको एक प्रॉब्लम दिया गया है कार्टिशियन कोऑर्डिनेट में पॉइंट बैठा के, लेकिन तुम उसको जब तुम सिलिंड्रिकल में देख रहे हो, रियलाइज कर रहे हो, तो फिर एनालॉजी होगा कि कार्टिशियन से सिलिंड्रिकल कोऑर्डिनेट सिस्टम में कैसे कन्वर्ट करना है, तुमको फॉर्मूला पता है। लेकिन तुम अगर सिलिंड्रिकल कोऑर्डिनेट सिस्टम को अपनी तरीके से ओरिएंटेशन करना चाहते हो तो भी कर सकते हो, एज पर द रिक्वायरमेंट ऑफ द प्रॉब्लम। So this example illustrates how equation number 12 is applied to a straight, thin current carrying conductor. The key point is keep in mind in applying the equation number 12 is figuring out alpha 1, alpha 2, rho and unit vector phi to find h at point 005 due to the side 1 of the loop. Consider figure B, okay, 6B, where side 1 is treated as a straight conductor. Notice that we join the point of interest 005 at the beginning and end of the line current. Observe that alpha 1 and alpha 2 and rho are assigned in the same manner as figure 5. That means they are assigned in the same manner here also, like this, here also they are assigned in the same manner. If I remove this part, you can see here also alpha 1 alpha 2 are assigned in the same manner. पहले फिगर में क्या था, हम वापस जाते हैं, नीचे वाला जो पॉइंट था वहां से h का जो डिस्टेंस एंगल है, h को किस एंगल से वो रिप्रेजेंट कर रहा था, वो है अल्फा 1, और एंड पॉइंट से h का जो लेंथ है, h का जो पॉइंट है वो किस एंगल से पॉइंट कर रहा था, वो है अल्फा 2। ओके, सो दिस इज अल्फा 1 एंड दिस इज अल्फा 2। तो ये है पॉइंट, जो नीचे वाले हिस्से से जो एंगल प्रोड्यूस कर रहा है वो है अल्फा 1 90 डिग्री, और एंड वाले हिस्से से जो प्रोड्यूस कर रहा है वो है अल्फा 2, दैट वी डोंट नो। सो लेंथ इज 2, सो द वैल्यू ऑफ द लेंथ ऑफ द कंडक्टर इज 2 यूनिट, current is 10, okay, that we will put, okay. So alpha 1 is 90 degree, so it is 0. Alpha 2, so alpha 2 का वैल्यू क्या होगा, क्योंकि ये जो है रो का वैल्यू क्या है, रो का वैल्यू हमको पता है कि 5 है ना, 5। तो अगर दिस इज सो दिस इज द राइट एंगल ट्रायंगल, इज द बेस, ओके, सो वी वांट टू फाइंड आउट द वैल्यू ऑफ अल्फा 2, ओके। So we can easily, we have the value of base and perpendicular, so we can directly write tan alpha 2 equals to 2 by 5, base by perpendicular, so therefore alpha 2 is equals to tan inverse of 2 by 5, ठीक है, 2 by 5 आ गया, और cos भी कर सकते हैं हम लोग हिसाब से, ठीक है, ये ऑलरेडी वही किया गया है, यहाँ पे कॉस निकाला है। सो कॉस क्यों निकाला, क्योंकि कॉस का वैल्यू वो चाहिए, दैट इज व्हाई इट इज डन, ओके। सो कॉस का वैल्यू चाहिए हमको, तो कॉस अल्फा 2 मतलब कॉस अल्फा 2 बेस बाय हाइपोटेन्यूज, बेस क्या है 2, हाइपोटेन्यूज क्या है ये वाला, इसका क्या है वैल्यू होगा 2 स्क्वायर प्लस 5 स्क्वायर, दैट इज root over of 29, so it is root over of 29, okay. So this is root over 29, that is written over here, so we will put this value over here in this equation। तो इक्वेशन था हमारा ये वाला 12, okay, so that we will be putting, and we will get the solution. Now we have missed out one thing, that unit vector phi will be there, we have to also locate unit vector phi, so where is phi, unit vector 5. In unit vector 5 we know that if you compare with this particular diagram, okay, figure, the unit vector 5 will be the cross product between unit vector rho and L or Z, okay, unit vector rho and L, okay. So now over here this is unit vector rho, this is unit vector rho, unit vector L, that is the length actually. So L can be in Z axis, X axis, Y axis, whatever. A rho can be also in any axis. But if you multiply them, if you find the cross product, you will find the value of unit vector 5. So we are just writing unit vector 5. Okay. Now actually unit vector 5 will be in the minus Y axis because we have to represent in Cartesian coordinate system. माइनस वाई एक्सिस पे होगा क्यों? क्योंकि यहाँ पर देखो ये था एक्स एक्सिस, ये जेड एक्सिस, ठीक है, तो ये बाकी क्या रहा? बाकी रहा वाई एक्सिस, तो वाई एक्सिस में होगा, लेकिन माइनस वाई में होगा क्योंकि क्या हो रहा है कि रो यूनिट वेक्टर रो क्रॉस यूनिट वेक्टर एल, दैट इज द फॉर्मूला. इफ यू सी दिस वन, सॉरी, एल क्रॉस रो, सॉरी, L cross rho, okay, L cross rho, L is X, so X cross unit vector Z, it is given actually unit vector Y minus Y, okay, because unit vector Z cross unit vector X gives you Y, okay. ये भी वो राइट एंगल, सॉरी, राइट हैंड थंब रूल से होता है कि परपेंडिकुलर होता है, ठीक है. X के साथ इसका अगर क्रॉस करोगे तो यूनिट वेक्टर यहाँ पर निकलता है y के डायरेक्शन में, ठीक है, y एक्सिस. Okay, so understood. So it is quite easy. So the question was very simple, that you have 3 conductors, but you will take only one conductor and you will find the magnetic field intensity at a point 5 due to the one conductor only. So you will take only 10 ampere because same thing, all the current is same. So the only effect of this particular conductor, the magnetic field intensity due to effect of only this particular conductor. Okay. That you have to find out. So that was quite easy using that particular formula. So this equation you have to take. Okay. This equation you have to take. You have to find out the value of alpha 1, alpha 2. Just replace those values. You have the value of I, you have the value of rho. Replace. And you have to understand that L is in which axis and rho is in which axis. If you look at, then obviously the third coordinate will be the other axis. The result will be the third axis. That is the solution. Okay. Okay, so any questions regarding this particular numerical? You can ask. Have you understood? Okay, so you then go through this. Okay, so I will be telling you the syllabus for this second internal. Okay, because okay, by the end of this day I will be sharing in the Google Classroom. Okay, so you must see the Google Classroom. Okay, okay, so in this first half itself I will be giving you the syllabus. Okay, okay, in the first half before 12 I will just, tell you the syllabus. So whatever it was done, it was there in the first slot, that portion will not be there, but up to which portion will be there, that I will be giving you. Okay, okay, so then thank you students. So we will be joining in the next class because next week also we have the classes. Okay, so thank you.